Hi everyone, and welcome to Eric's Electronics Workbench. So the project on the bench today is a military radio, the RT-834, which is part of the GRC-106A HF radio set. Now I've already removed the RT-834 from its case. So the RT-834 is a transceiver and can be used as a standalone receiver or with the AM3349 RF amplifier for transmitting. So the RT-834 is similar to the earlier version RT-662, but the RT-834 has the added 100 Hz tuning steps plus some other minor changes. This knob over here is 100 Hz tuning. When the AM3349 is used with the RT-834, the letter A is added after GRC-106, as compared to using the RT-662, which would not have the A designation. This radio set covers from 2 to 29.9999 MHz in AM, upper sideband, FSK or frequency shift key, and CW or continuous wave. Tuning is accomplished by setting the front panel dials to the desired frequency. So that's all of these dials across here, and the numbers are in these little windows across there. Tuning information is also sent to the AM3349 via the front panel PA connector. With the AM3349, the RF output power is 200 to 400 watts depending on the mode selected. The RT-834 by itself only outputs about 125 milliwatts RF power, which is intended as a drive for the AM3349. This radio was manufactured under a 1967 contract by Magnavox Company out of Fort Wayne, Indiana. There were other manufacturers of these radios such as Cincinnati Electronics and General Dynamics, and they are all identical as they were all built to the same military specs. The RT-834 is an electromechanical marvel with a motor, gear trains, switches, relays, transistors, vacuum tubes, and even some integrated circuits. So we're looking at the bottom of the chassis. This is the front panel. You can see here's a motor. It drives these gears, which is part of the tuning system. And then there's some shafts that come down right here. Those are linked to these knobs on the front panel. So if I turn this knob, for example, you can see how it's rotating these beveled gears. It goes across, rotates those beveled gears, ends up driving into that module. And inside the module, there's some switches. It's part of the tuning system. If I turn this knob right here, it's rotating a shaft with some beveled gears all the way over to this point. If I rotate this knob right there, there's some gears right there. It comes down, some beveled gears inside. It's coming all the way over and driving down into some gears in this area here. Turn like that. This gear over here is rotating, so quite a mechanical system for the tuning in this radio. These four modules contain electrical switches and tuning circuits that are mechanically coupled to the drive mechanism we saw on the underside of the chassis. Now this RF amplifier contains a large turret assembly that is driven by the motor. The electronics are stationary in the center of the module. And you can see the two vacuum tubes. So this is a 6BZ6, this one is a 6AN5WA. And the turret assembly rotates around the outside like so. The turret contains tuned circuits that are selected in 1 MHz increments. The selected tuned circuit section makes contact to a set of stationary contacts, thus retuning the RF amplifier section in 1 MHz steps. The motor can only drive in one direction, so advancing up in frequency, say from 10 to 11 MHz, is fast, but from 10 to 9 MHz takes longer since the turret has to make almost a complete revolution. There's a little window right here. It says 10 in that window, and then megacycles or megahertz. And that means that this was last tuned to 10 megahertz. And the reason that this is visible here is just for aligning this when you're working on it so that you know what frequency the tuned circuit is set to. So if this was incorrectly set, then obviously the tuning would be way off. And there's a diagram here that shows a section of what's on the turret assembly. So there's one of these for each 1 megahertz band. And these components are used to create those tuned circuits. You can see this chart right here and the different frequencies and which components come into play. Now I've noticed several test point jacks on a couple of the modules are loose, possibly a cracked solder, so those will definitely need to be repaired. So this test point right here marked DC lock volt, and several over on this module. But the main fault is that the radio has a receive and transmit frequency problem, so let's take a closer look at that. So let's take a look at the problem this RT-834 is having. So I have it connected to my Keithley power supply. The power supply is set to 26 volts DC, and as a safety precaution it's set to current limit at 2 amps. Now this radio requires between 24 and 28 volts DC, and it's fused at 2 amps. This is a spare fuse holder. So whether this is transmitting or receiving, it won't require anything more than 2 amps. And you can see the test leads going off to the power supply. They're clipped on the pins in this power connector on the front panel. Now when this is connected to the RF power amplifier, that amplifier will draw between 40 and 50 amps at 24 to 28 volts DC when it's transmitting and generating that 200 to 400 watts of RF output power. But again, this portion, just this radio, requires no more than 2 amps. And it's been on for about 20 minutes now and had a chance to stabilize. And right now the radio is drawing 1.4 amps, and it's just in the AM receive mode. So the first thing that I wanted to check is that this frequency standard, the ovenized crystal oscillator, is working correctly. So this BNC connector on the front panel is an output, should be 5 megahertz. So I have this going off to the frequency counter. And there's some test points right here. There's a 500 kilohertz and also a 10 megahertz output, and I've tested those as well, and also a 1 megahertz output, and I tested those. No problems whatsoever. They seem to be working, except that these are very loose in here, and that's when I noticed these test points were loose, and I started looking at the others as well. So even though they're loose, I was able to get a reading off of them. So this does seem to be working correctly. But again, the 5 megahertz output is at the front panel. It's also right here. So I'll move you up to the frequency counter and take a look at the result. Right there. So it looks very good. I don't see any problems with that. So very, very close to 5 megahertz, just some change on the end. And I might try to dial that in a little bit closer on the frequency standard. There is an adjustment that would probably dial that in a bit closer, but I don't see any issues with that. And the value that we see there certainly wouldn't cause the radio to perform incorrectly. And on the left-hand side of the screen, you can see the Keithley power supply, again 26 volt output, and the radio is drawing 1.4 amps. So all looks good, no issues going on there. So let me just move you back down here, and I'm going to go over to this RF amplifier module. Pardon the movement here while I get this set up. So just as an example, when the radio tunes, if you look in this area right here, you see some contacts move past. It's set to 10 megahertz right now, so I'll go to 11 megahertz. So I'm just turning the ones digit on the megahertz dial, and you can see that clicked over. Some movement right in there, and you can't see it here, I don't think from the camera angle, but there's you can see the contacts move past there, but you should be able to see them right here. Okay, now I'll tune back down to 10 megahertz, and remember, tuning down usually takes longer because this has to make a complete rotation. So we'll go back to 10. And you can certainly hear the motor running in there. You can probably see the contacts moving past right there. Now the actual stator where those contacts are making electrical contact is right over here. So this is just visible, but there's no electrical contact going on in this area. So when I do the test, you're going to hear that motor run because the problem happens when it tunes and then retunes again, and I'll explain a little bit more about that. But again, you're going to hear that motor run. And let me just move you down to the front panel, and I'm going to reach around here. Sorry, it's so dark. Get this touched up a little bit here. Brighten this up a little bit better so we can see what's going on. So just looking at the front panel, again, you can see this is at 10 megahertz. So when I go to 11 megahertz, you can see that goes right there. And then if I go back to 10, if I go to 20, back to 10, if I go to from 10 to 11, 12, 13, back to 10. So you get the idea how the motor runs in there, and you can certainly hear that operation. Now there's no problem with the tuning on here, except that when it does a retune, the problem occurs, but I don't think the problem has anything to do with that motor or those RF amplifier modules on the turret or anything like that. But I will be moving these, and I'll explain the positions that those are in when I do that adjustment. And over here, the kilohertz knobs, no problems here. Again, these are mechanically linked into those modules. You can certainly hear a clunk when those turn. And the position of these has nothing to do with the problem. I don't see any relation there. But the problem happens over here on this 100 Hertz adjustment. So this is just an electrical switch. There's no mechanical link into any modules. So it was at 0, now it's at 100 Hertz, 200 Hertz, 300 Hertz, and so on. And I'll be moving this, and I'll explain the position of this and where it's at when I do the test. Okay, so keeping all that in mind, I'm going to put the camera over on the Hewlett-Packard 8920A RF communications test set, and I'll just leave the camera pointed at that test set, and you can see the results on the screen. I'll connect some cables, and we'll run the test, and you'll see the problem right away. All right, so on the 8920A, we'll start with the receive test. So this is a signal coming out. This is acting as an RF signal generator. So it's set to 10 megahertz output. The amplitude is minus 80 dBm. And it's set to AM modulation with a 50% modulation and a 1 kilohertz tone. And I think everybody has a good idea about what a 1 kilohertz tone should sound like. I'm going to go over to the radio. I'm going to turn the volume up on the radio. And you hear that sound? Okay, that's not a 1 kilohertz tone. Turn that back down again. That's definitely not 1 kilohertz. Okay, so I'll turn that back up a little bit there. That's clearly off frequency. Right? That's not how it should sound. If that was a voice signal, it would be very, garbled and really unintelligible. Now what I'm going to do, I'll leave the volume turned up so you can hear it a little bit better. I'm going to start increasing the 100 Hertz control. So right now the radio is set exactly at 10 megahertz, okay? But I'm going to start increasing that 100 Hertz control. Listen to what happens to the frequency. There's 1, so 100 Hertz higher, 200, 300, 400, 500, 600, 700. So I'll turn the volume back down on the radio. That's a big jump all of a sudden. That wasn't right. Now it's off frequency still because now we've dialed it up by 700 Hertz higher, but now I'm going to take that control and turn it all the way back down to 0. Hear that tone? That's much closer to a 1 kilohertz tone. Now the dial is right on 10 megahertz again, where we started, but before it wasn't a 1 kilohertz tone, it was off frequency. So essentially the radio doesn't lock on to the right frequency until you fiddle with that 100 Hertz control a little bit. You get it up to about 700 Hertz off frequency and suddenly it locks in, all right? And then it's good to go. I've set it back down to 10 megahertz and everything is perfect and it's receiving no problem. Now watch this. And I'll tune up to 11 megahertz and then back down to 10. So you'll hear the motor run again. Okay, there's 11 megahertz. I'll retune back down to 10. Problems there again. It's off frequency, right? That's not a 1 kilohertz tone. And if I go back and I turn the 100 Hertz control back up, 1, 2, 3, 4, 5, 6, 7, there it is. Locks again, turn it all the way back down to 0, we're good to go. And just to show the other controls really have no effect, I'll retune it again, go to 11, back down to 10. It's off frequency again. 1 kilohertz higher, 2 kilohertz higher, 3, goes completely silent. That's all the way up to 9 kilohertz off. It never does relock on, right? That's back to the 10. There's 10 kilohertz off, 20, 30, 40, 80, 90. All the way back down to 10 megahertz again. But it's not causing it to lock back on. 100 kilohertz, 200, 3, 4, 5, 6, 7, 8, and 9. All the way back down to 0. It never did relock onto the frequency. But if I just reach over and turn the 100 Hertz control up, there's 700 Hertz. Good to go. And it locked back on. Really an unusual problem. but it seems to be only related to the 100 Hertz control. And there's a module specifically dedicated to that 100 Hertz control. So I think that module is the first place to start looking. But there's a little bit more to it. Let's take a look at what happens when we transmit. So I'm going to move some cables around here, and I have the microphone, so I'll key the microphone. You'll hear my voice actually come through on the RF test set because it'll demodulate the signal, so it'll show that the radio is actually transmitting and modulating correctly. But watch what happens with the frequency. It's a little bit unusual. All right, now let's see what happens when the RT-834 is keyed and goes into the transmit mode. So I have the 8920A in the transmit test setting. It's set to auto-tune, so whatever the carrier frequency is, it'll just lock onto that, and it'll display that value up here. Right now, these numbers are meaningless because I'm not transmitting. And right here, you can see it's set to the AM demodulation. Now, I just want to emphasize that this is acting like a dummy load, so in no way is this radiating out any RF power because 10 megahertz is not an allowed frequency that you can just transmit on. It's not an amateur radio frequency, so you would not want to key the radio and be transmitting on an actual antenna on this frequency. So again, there's no radiated power because this is absorbing all of it. It's acting like a dummy load. All right, so first of all, on the radio itself, it's on 10 megahertz. I'm just going to retune it just for clarity. So we'll go like this. Go to 11, and back to 10. Okay, so this is in the position that in the receive mode, it was not working right. It was off frequency, okay? Now I'm going to key the transmitter. And we have about 100 milliwatts. That looks perfectly fine, no problems there. You can even see as I'm talking right now, it's jumping around with the AM modulation, the AM depth. And look at the frequency though, that looks really good. 9.999 and 8. It's very, very close to 10 megahertz. So I really wouldn't see a big issue with that. It's off just a little bit, but I mean, it's really close. And if I go over here and turn the volume up, you can hear my voice coming in right there. You can probably hear it behind my regular voice. Bring the microphone a little bit closer right there. But yeah, I mean, it's certainly modulating the carrier, no problems. It's getting some feedback actually into the microphone as well there, so I don't want to turn that up too loud, but I'll unkey the radio. So now, again, these numbers are meaningless at this point. But that looks fine, there's no problem. So it's off on the receive, but the transmit seems to be acceptable. But now watch this. On the radio, I'm just going to turn the 100 Hertz control up to 700 Hertz, okay, right there. And now I'm going to dial it back down, okay? So when I did that, now on the receive mode, it was working correctly. Now I'm going to retransmit or rekey the radio and transmit. There we go. Look at the frequency, it's further off now, 9.998, it was 9.999. Transmit power looks to be fine. Again, talking into the microphone, I see some AM modulation. Turn the volume back up again. No problems there. You can probably hear my voice behind the normal voice. So, I mean, it is working correctly, and I'll unkey it there. As far as transmitting, but the frequency seems to be further off when it's actually receiving okay. So the two are just flipped opposite each other. If it receives okay, it doesn't transmit quite on frequency. If it transmits on frequency, then it doesn't quite receive. So just for the sake of completeness, before I start disassembling any modules, let me just show you on another random frequency what happens when I transmit. And I've tried the transmitting and receiving on many different frequencies, and the problem is everywhere. It's not isolated to any certain bands or any specific frequencies. So right now the radio is still set on 10 megahertz where we were testing it, but I'll drop it down to 3 megahertz. So I'll go like this and... Okay, so it retuned, so it's right on 3.0000, and I'll key it. So transmit, so there it is, it found the carrier, and 2.999 and then 8, it's very, very close to 3 megahertz. RF power looks okay. So no issues there, it's perfectly fine. And then if I go to 3.1, key it again. Yep, very close, 3.0998, so pretty much 3.1, we're very close on that. Let's try, say, 3.12. Key the transmitter. Yeah, 3.1 and then 2. Yeah, I could see that. That 9 would carry over then to the 2. Very close. And let's go 3.125 right there. So 3.125, and then the 100 hertz control I haven't touched yet. It's still at 0. Key the transmitter. So 3.12 and then 4, but 8. Yeah, it's very close. I could see that. It's pretty close to 3.125. Just ever so slightly off, but seems very, very close. Okay, now I'll take the 100 hertz control and I'm going to turn it up to 7 like we did before. And now back down to 0. I'll key the transmitter again. Oh, that's way off. 3.1233. So that's a lot worse. I'll unkey the transmitter again, so now the numbers are meaningless. It's not transmitting. But if it was in the receive mode, that would be receiving perfectly fine now. In fact, let's try that. Let's go back to receiver test. And I just move this back over to the receive in, that. And let's go frequency. Let's just see what happens here. So this was on 3.125, so we'll go 3.125 megahertz. I'm going to turn the volume up. Perfect. That's a 1 kilohertz tone. So because I had turned that 100 hertz control, it caused the radio to lock in. But on transmit, it's way off. So it's very unusual. You can either get the transmit frequency right or you can get the receive frequency right, but you can't do both. And it always gets affected by that 100 hertz control. But again, I'm going to start in with the 100 hertz module and open that up, and let's have a look around in there. I removed this cover from the bottom of the radio. So this cover just fits in here like so. And the purpose of this cover is just to protect the wiring on the bottom side of the chassis. And when you look at how beautifully this is constructed, all the wiring is very neatly loomed all throughout. And remember, this would have been entirely hand-built. So very impressive construction, very, very different from how you would see something manufactured nowadays. So this is the 100 hertz tuning module, and the switch on the front panel that has the 100 hertz tuning steps electrically connects only to this module. So I think this module would be a good place to start the troubleshooting. However, I noticed that there's a power supply right here that supplies 5 volts DC to this module. And power supplies are always a good thing to start checking first, because if the voltage is wrong, then of course the circuits are not going to work correctly. So let me grab my digital multimeter and we'll check that power supply. Set that to DC volts. So the voltage is referenced to the chassis of the radio, so I'll just touch the negative probe on the chassis. And this white wire right here appears to go around to the module, so that should be the output from the power supply. So just reach down in here, the radio is already turned on. Right there. And yes, looks good, 5.02 volts. So no problems there, definitely has the correct voltage going to the module. So let me get this module removed and opened up, and let's have a look inside. Alright, so I disassembled the 100 hertz tuning module. It contains these 2 circuit boards, and I noticed a mix of analog and digital circuitry inside this module. Now, I have the module flipped over and reconnected into the radio, so there's 4 coax cables and some wiring going up to this other connector. That way I can power up the module in the radio and start some troubleshooting and taking some measurements. Now the module is sitting on this notepad just so that it doesn't short against any wiring down in the chassis. And to the extent that the module has been disassembled, I don't see any damaged components or broken solders, but I need to take a closer look at this bottom circuit board, as well as start measuring capacitors and resistors and things like that. But I noticed that there's a multi-turn potentiometer right in that corner, and I thought, well, since there's an adjustment in this module, I wonder what the service manual has to say about that adjustment and maybe any measurements that you could make on the module. So I'll put those instructions up on the screen. You can take a look, but I think there's a typo in those instructions. So taking a look, there's step 1 and then A through F, and then go down to step 2, section B, and it says to connect the oscilloscope to terminal 1A, 1A, 2A, 8A, 1E2. They have the craziest long reference designations in the service manual, but essentially that's terminal E2, and that's where the oscilloscope probe is connected. It says to set the sweep rate on the oscilloscope to 0.2 milliseconds per centimeter or per division, and 0.2 milliseconds is the same as 200 microseconds, which is what my oscilloscope is set to. And then on C it says to set the 100 Hertz frequency selector switch to 0, which it is. And that's the same setting on the radio where it doesn't receive correctly and it's off frequency, like we saw earlier. Then it says to turn potentiometer R8, another very long reference designation, but that's that multi-turn potentiometer, clockwise 12 turns. I have not touched it. I don't want to do that yet until I look at other components, because if there's a failed component elsewhere, making any adjustments would never work out correctly and it might just mask the problem. So then moving along to E, it says to adjust the potentiometer R8 until the bottom half of the square wave on the oscilloscope is 600 milliseconds long, or 3 divisions, or 3 centimeters. That can't be right. 600 milliseconds is over a half second long. I think what they meant was 600 microseconds, or 0.6 milliseconds. And then it says the top half of the square wave should be 400 milliseconds long. Again, I think a typo, probably 400 microseconds long, or 0.4 milliseconds. The times that are given there just don't work for the circuit and what we're looking at. So I'll move you up to the oscilloscope and you'll see the waveform. But the waveform also doesn't look anything like what they're describing here, as far as the top and bottom being a little bit different. So pardon the camera movement here, I'm just going to move this up to the scope. And pardon some of the flicker that you see on that CRT. I don't see that with my eye when I look at the screen, but it picks it up on the camera. However, you can see the waveform, somewhat of a square wave there, but it's very unstable. It's not that it's not triggering properly, it's just a very unstable waveform that's going into the oscilloscope. And that's of course why this radio isn't working properly. It's not supposed to be doing that. Now if I take the 100 Hertz control, it's at 0 right now, and I'll go to 1, and you can see it kind of changed it a little bit, but it's very unstable. Go to 2, go to 3, okay, go to 4. That actually doesn't look too bad. In fact, I'm thinking that might be close to what they were describing, because you have 2 divisions and then there's actually 3 divisions, close to 3 divisions on the top. And looking back at the instructions, yeah, it talks about it would be 3 centimeters. So that actually might be pretty close in how it looks there, but it's not right, because if I go to 5, it jumps again, I think there, yeah, it jumped a little bit. But then if I go to 6, it's unlocked again. So it might be somewhat okay on those frequencies, but then it's not stable. I'm just going back between 4, 5, 6. Okay, I'll go to 7. Now remember, at 7, the radio started working much better and would lock in, and that's at 700 Hertz right now. Go to 8, and there's 900 Hertz. Now I'll go all the way back down again. That's 0. So now it's locked in at 0. See, it was very unstable there before. It is stable at this point, but now the waveform doesn't have the right time compared to what they're saying in the instructions. And if I start increasing, there's 100, 200, 300, 400, 500, 600, 700, 800, and 900. So there's a little bit of a change in every position, so I don't think it's an electrical problem with the switch on the front panel. But again, the time doesn't seem right. In fact, if I go all the way to 9, you know, we have a really long duration here, much shorter here. And if I go all the way down to 0, that's not even close to the times that they're giving you know, in the instructions. So definitely an issue going on there. Now if I go over here to the megahertz control, I'll just cause the radio to retune. So you hear the motor run. Okay, there's a new frequency, but did you see how the waveform dropped basically to 0? And I think what's happening is the module gets turned off during the tuning cycle, and then when it turns back on, it's unlocked again, and you know, it starts all over. So it's at 0 right now, and if I increase it, there it starts to lock in, go down, now it unlocks. But if I go, oh, it's a very different looking one there. That's at 5, but look at how that looks very different. So it's not very consistent at all. Nope, and then that looks different yet again. That's at 400 right now, 4 on the dial there. So yeah, it's really all over the place. But there's 7, there it starts to lock in, and I'll go back down to 0, and it's locked in like before. So even though it's locked in, the waveform doesn't look right for the times involved. So I removed the 100 Hz module circuit boards from their case, and you can see that right here. So there's a filter on the side of the case, 3 wires attached to it, so just desoldered those. And with the circuit boards removed, I started testing components, looking at capacitors, resistors, transistors, diodes, and so on. And really none of the components stood out as being a problem. And then I tried powering up these boards away from the radio. So if you apply 20 volts and 5 volts, the circuit starts to come to life. There's a 15 volt regulator on the board as well. I checked that it's working properly. And I noticed that with voltages applied, that the VCO, which is a voltage controlled oscillator, starts operating at its free running frequency. Waveforms look perfectly fine around the VCO. Started making some DC voltage measurements around the circuits as well. Nothing stood out as being a problem. So I thought, is there a way to test this module with perhaps putting in a known signal and taking some measurements? So let's go over to the block diagram and I'll show you what I figured out, and then I'll show you what's going on here. All right, so here's the block diagram for the 100 Hz module. Also, there's a typo on the diagram. You can see right here the pulse shaper is called out as A1Q1, and the phase detector also says A1Q1 for the reference designation. It's correct on the pulse shaper, but this phase detector is a different component. So we start over here with a 1 kilohertz pulse, and this is coming from the frequency divider module. This is really the reference that's going into this module. So this 1 kilohertz comes into a pulse shaper, cleans up the signal. That 1 kilohertz comes up to a phase detector. Now, going around here, this is a PLL phase lock loop. And PLLs are notoriously difficult to troubleshoot because a problem can show up anywhere around this loop. Sometimes you have to break that loop to really isolate where the problem is at. But out of the phase detector, comes up with a 1 kilohertz signal that is going to the DC amplifier and inverter, over to a low-pass filter, which basically removes any AC component. And you have the DC frequency correction voltage that goes into the VCO. So the VCO is a voltage-controlled oscillator. So it has a free-running frequency, and then that frequency can be manipulated or adjusted by this DC voltage. And the output from the VCO should be 110 to 119 kilohertz, and it'll be at a specific frequency depending on where the front panel switch, that 100 hertz frequency control, is set to. So in the example here, this is set to 300 hertz, so it's 0011, that's the binary for 3. And so when that happens, this range from 110 to 119 kilohertz ends up sitting at 113 kilohertz. So when it's at 110, that would be when the switch is at 0, and 119 kilohertz is when the switch would be at 9. So the output from the VCO goes into another pulse shaper, and it goes 2 directions. It goes this direction over to the divider, which is a whole bunch of digital logic, and it's programmed by that front panel switch. And this divider will divide down so that whatever this frequency is here, it ends up coming out as 1 kilohertz. So for example, if this is 113 kilohertz, if that's the desired frequency, then this is going to divide by 113, and you have 1 kilohertz coming out. Now that goes back to the phase detector. So the phase detector has 2 inputs, and the output of the phase detector is proportional to the frequency and the phase. So essentially what happens is this 1 kilohertz pulse coming in is the reference, and this phase detector will make the correction so that the voltage over here going into the VCO corrects its frequency to hold it so that this is 1 kilohertz. So if the 1 kilohertz here rises up or down, this makes the adjustment, corrects this voltage, and it keeps this loop right on frequency. Okay? Now the pulse shaper also has an output that comes down to a decade divider, which decade means 10, so this is dividing whatever this frequency is by 10. Again, in their example here, it's 113 kilohertz going in, you'd have 11.3 kilohertz coming out. A balanced mixer, so this input right here is coming from the 10 and 1 kilohertz synthesizer module. We have some mixing going on. It goes to the 7.1 megahertz amplifier and filter. That filter is what you saw on the side of the case. Then the output comes over here to an emitter follower, and it makes its way off here to the 100 kilohertz synthesizer module. So my thought was, how could I test this, at least a good portion of this circuit, to see if it's working correctly, especially this PLL. I was a little bit concerned about that. Well, it turns out that if we take a known 1 kilohertz signal coming in, and I'll use my function generator for that, I have it set to create a 1 kilohertz pulse. So we have a known good steady 1 kilohertz signal coming in. Then we can set this front panel switch because the module is plugged back into the radio for power and the connection to that switch. So we can make the adjustments on the switch, and we can look at the output over here. And really what actually matters is this signal right here, this frequency going into the balanced mixer. Does this signal sit in this range right here, and does it adjust accurately and the way that it's supposed to? So let's go back over to the frequency counter, and I'll show you the result. Then I'll just show you on the circuit board where I have the connections for the frequency counter, and then you'll see the result that's going on. All right, so my idea is to start by testing the 100 Hertz module's PLL. So all the components that make up that PLL will be tested with this setup. So the VCO, the digital logic, everything else that we saw in that block diagram. And the output from the VCO goes through the decade divider, so I'll just monitor the output on the decade divider and see how that looks. Now earlier in the video we already saw that the PLL was very unstable and not locked until the front panel 100 Hertz switch was set to 7 or 700, and then it seemed to lock in. Now this test setup won't check the action of the mixer in the final output stage, but one thing at a time, let's just start with the PLL. So right now this is all powered up in the radio, so we have power coming in on this connector, as well as the binary count from the 100 Hertz switch, and that sets this digital logic over here. So I have a 1 kilohertz signal coming in right here from my function generator, and these two connectors are electrically connected together so the signal could go in on either one. Now in the radio, the signal just comes in on one connector, passes through and goes out the other, and there's some circuitry right here that's just picking off the 1 kilohertz pulse for monitoring. And this test probe right here is connected to a little resistor, and that's on the output of this decade divider integrated circuit right there. So taking a quick look at the schematic right here. Here's the input for the 1 kilohertz pulse. You can see the two connectors are electrically connected together. And down here is the decade divider, so I'm monitoring the output right here on this resistor. And then this goes off to the mixer over here and so on. So again, we're not checking the mixer or this part of the circuit here, or this stage right here, but this decade divider, the VCO, and all of the digital logic over here. So what we should see on the output from this decade divider right here is that it goes from 11 kilohertz to 11.9 kilohertz, and that should step as I go through the settings on the 100 Hertz switch. So right now the 100 Hertz switch is at 0, so the output should be 11 kilohertz. Let me move you up to the frequency counter. And actually stop over here, you can see there's the function generator for the 1 kilohertz pulse. But here's the frequency counter, and check it out. It is 11 kilohertz. It's spot on, no problems. So now let me go over to the switch here, and I'll go to 1, so that's 100 Hertz. And so it should be 11.1, and yes it is. Now there's 200 Hertz, so that's 11.2, perfect. There's 3, so that's 11.3 kilohertz, yes. There's 4, and yes, 11.4 kilohertz. There's 5, yep, 1.5 kilohertz. There's 6 on the switch, and yes, 11.6, perfect. There's 7, and yep, we've got 7, 11.7 kilohertz. There's 8, perfect, looks good. And there's 9, and yes, perfect, 11.9 kilohertz. So that's very good to see, no problems there. Let's take a look at the waveform. I'll just leave that where it is on the 9. Let me move you down to the oscilloscope here, pardon the movement. Brighten this up a little bit here for you as well. Just move this probe down here. All right, so that's the output from that decade divider. It looks great. I don't see any problems there. Spot on. Now, if I change the setting, so it's at 9, and I'll turn the switch all the way back down to 0, you don't see a lot of change on there because the frequency steps are pretty small. But through each of the settings, the switch, the waveform looks good for each setting of the switch. I'll just go through them here. You can see how it's jumping a little bit as I change it there. And there's all the way back to 9 again. So perfect, I don't see any problems whatsoever. And again, the ultimate goal of this whole circuit is to generate that range of frequencies on the decade divider. And it certainly can do that. I don't see any problems. It's not unstable or anything, you know. So let me go back over here, because when it would retune, that's when things would unlock again. So it's at 0, and I'm going to turn down here to retune it there. Back again. Perfect. It locks back in. So I'm suspicious of the signal that's coming into this module, because the module seems to be working correctly when I give it a good reference 1 kilohertz pulse. You know, it's a known good signal. It's not having any problems at all. But it sure has problems when it's connected into the radio. So let's take a closer look at the signal that's coming into this module and see what's going on. All right, so I'm checking the 1 kilohertz pulse output from the frequency dividers module. So this is the 1 kilohertz pulse that goes into the 100 hertz module that we've been testing, and it's the 1 kilohertz pulse that I replaced by using my function generator. So you can see I have the oscilloscope probe touching the center conductor of that connector on the end of the coax. So this connector is what would plug onto the 100 hertz module. And, well, take a look at the oscilloscope. Not exactly what I was expecting to see. Let me get this touched up for you a little bit so you can see this better. So that signal looks perfect. There's nothing wrong with that. So the amplitude is correct. It's supposed to be 1.5 volts peak to peak, plus minus 0.5 volt, and it's within that range. And the frequency is spot on. Look at that, right at 1 kilohertz. So I don't see any issue whatsoever with that signal. But how can this be? When that signal is applied to the 100 hertz module, it becomes very unstable. But when I apply essentially the same signal from my function generator, the module has no trouble and the PLL locks. Since I just saw a good 1 kilohertz pulse on this coax coming from the frequency dividers module, I reconnected it to the 100 hertz module, but I want to monitor this signal coming into the module. So I have the oscilloscope connected to this other connector. Now remember, this is a pass-through between these two connectors. There's just a trace on the board linking them. So whatever signal is appearing on this coax and going in the module will go onto this connector and go off to the oscilloscope. So let me move you up to the scope and you can see the result. Get this touched up a little better here so you can see the screen. That's nothing like the 1 kilohertz pulse that we saw when the coax wasn't connected to the module. So for one thing, the amplitude is wrong. This is only about 0.5 volt peak to peak, so much lower than we saw before, and the pulses are extremely narrow. Now it does show the frequency is 1 kilohertz, but it says unstable histogram. You know, the amplitude is jumping around a bit, but I don't see that the frequency is shifting, so it does look to be stable like it was before. Now let me reach around here, and I'm just going to increase this. So if we take a look here, the signal didn't seem to do this when I had the function generator connected. I don't see any problem with the input circuitry on the 100 hertz module, and I've already checked those components. Everything seems to be fine. I certainly don't see any low resistances or short circuits or anything real obvious that stands out. So I think the next step is going to be to take a closer look at the frequency dividers module and the 1 kilohertz output, see if there's an issue going on there. So back at the 100 hertz module, we can't forget about this other coax. This coax goes to the 10 and 1 kilohertz synthesizer module, so that's the 1 kilohertz pulse input to that module. Now this connector plugs onto this connection here, and that's the pass-through from this other connector. So it's just sending that 1 kilohertz pulse on downstream. So I have the oscilloscope connected to a capacitor, but it's on the side of the capacitor that just goes right over to this connector. So it's just monitoring the pulse that's right on this coax. So let me move you up to the oscilloscope and let's see what happens when I connect this coax onto that other connector. Get this touched up again. Alright, so I'm going to reach over here and just get this connection plugged in. Okay, right there. So it made the amplitude drop down a little bit more. So we don't have a lot of amplitude to start with there, and dropped it a little bit additional. So it looks like any further loading that 10 and 1 kilohertz synthesizer module is applying is just pulling that signal down even further. But I don't think the 10 and 1 kilohertz synthesizer module has a problem because it didn't completely kill that signal or do anything really drastic to it. So again, I'm pointing back to that frequency dividers module. I think that module may be the source of the problem. I removed the frequency dividers module. It's easy to do. There's just a screw on that corner, another screw on the other corner, and the module unplugs right off the chassis. So if I turn this latch on the top cover, and the cover should slide right off. There it goes. So there's 2 circuit boards on that side, 1 larger board on the other side, 2 connectors on the bottom. So join me in part 2 when I'll continue the troubleshooting on this frequency dividers module. So this concludes the part 1 video, and I hope you enjoyed the troubleshooting so far. And if you did, you can let me know by giving the video a thumbs up. And don't forget to subscribe because there'll be many more videos coming up in the near future. Lots of projects in the queue, and of course the part 2 video with this radio and continuing on with the troubleshooting. All right, as always, thank you for taking time to watch, and until next time, take care. Goodbye for now.